So let me set the stage. It's the first or second day of uni. The lecturer comes in and they say, "Hey, you remember that time where your high school biology teacher mentioned the amino acids to you? They just show you a list and they say, these are the amino acids. They make up what is known as proteins, and that's all you need to know about them. Okay, let's move on." Well, tough luck. It's university stuff now, and so you're gonna have to memorize each of the 20 amino acids, their names, their structures, and their properties. And you're gonna have to do it quick because we're gonna use this information for the next lecture, and you won't be able to understand anything if you don't understand the 20 amino acids. What we're gonna do for this video is I'm gonna try to attempt memorizing all 20 of the amino acids, and I wanna share with you what that process is like. And I think this will make for an interesting video because memorization is a pretty interesting subject. Like, I believe that there are two different types of memorization. One of them is blind memorization, and but these are like I made up on my own. By the way, there's no like scientist that came up with this. It's just me that came up with this based on like my own experiences. So there's what's known as blind memorization, which I would say is just you have a string of information and then you just read through that over and over and over and over again until it's in your head. So basically, the premise of that memorization is just based on continual repetition, and it's a quick, easy way of memorizing things, but the information will only be retained for I'd say a week, maybe even less. So it's not effective. Now, let's move on to the second type of memorization. This is what I call smart memorization. And smart memorization involves a lot of planning beforehand because you're not only going to think or put thought into what you're memorizing, but you also have to put a significant amount of thought into how you're going to memorize it. And that's what makes the key difference here is that there's planning, strategy, and technique involved in the memorization process, and that means that the information will be retained for a lot longer. So guess which type of memorization we'll be using? It'll be the smart one, because I need this information retained in my head for the next 3 to 4 years. So the goal of this video is I want to explain my thought process in a way so that if you are actively listening and also actively following along, then you'll also be able to memorize and understand these 20 amino acids the same way I will have. So the information that I internalize should be internalized by you as well, if I am explaining correctly and if I'm doing this right, which I hope I will be able to. Right. So this is not going to be an entertaining video. It'll be quite a boring one, but regardless of what reason you're watching, maybe it is with the intention of falling asleep, maybe it is with the intention of following along. Um, well, it doesn't matter honestly, right? Because views are still views. And even if the information about the 20 amino acids is not relevant to you, I will sort of be coming up with strategies and patterns, and maybe you could modify those strategies a bit so that it can apply to whatever is relevant to you. Maybe you're studying something or trying to memorize something. You could try to sort of follow my example if you think it will help. Right? I'm not saying that this is super good, this will help people. I just think it will or might help people. You might listen to what I have to offer and think otherwise, and that's all right. This is just how I memorize things, and I think it works for me. And if it works for other people, then good. I'm giving that information out there so that people can follow along. If it helps them, then super good. And if it doesn't, well, then that's fine too, right? Not everything works for everyone. All right. So, I want to begin with sort of a crash course on amino acids, because I think that will help people who are less familiar with amino acids to be able to follow along. Right, so what I have over here is a basic amino acid structure. So we have a carbon atom at the center, and we have an ammonium group over here, and we also have a carboxylic group over here. We have just a hydrogen, and we have an R group, which is variable. So the R group, that means it can be anything, and whatever it is decides what amino acid it will be. So for example, if the R group is a hydrogen atom, then the amino acid will be glycine. If it's a methyl group, then it'll be alanine, and so on and so forth. So every amino acid has the same basic structure, and the only thing that's different about them is the R group, or the side chain is what we call it. So when you're memorizing the structure of the amino acid, this part over here is not important, because the only thing that is different between the amino acid is the R group, so that's all you have to take note of. The R group is also what decides the properties of an amino acid. So the R group is really important, and this is how I represent it. The A is supposed to be the basic amino acid structure that is shared amongst all amino acids, and the only thing that is different, as you can see, is the group that is attached beneath the A structure. So that's how I have chosen to draw things. I also have the names written down. You can notice that some of them are red, some of them are blue. This means, so the blue means that there's nothing important or special about that amino acid, whereas the red means that there's something interesting to talk about there. I also have separated them into 4 different groups. We have small, and by that I mean small side chain. So you can see we have just an H, a CH3, just really small stuff in comparison to some of the others that we have over here. They're really long and really big. So that's what small means. We also have charged or polar. So that represents the side chain, whether or not it's charged or polar. So over here, for example, we have a negative on the side chain. That's why I put a negative over here. And a negative means it's charged, so we put it in the charged section. Over here we have a polar group. This section at the end over here with the double bond O is what makes the side chain polar. We also have another negative, and we also have a bunch of positives as well. And that's the charged slash polar section. Next we have the aromatic section, and this is given by the presence of a benzene ring. So you see all these things have in common. That's the benzene ring, and that's because the benzene ring is aromatic. We also have a hydrophobic section, and that is given by the hydrophobic properties or tendencies of the side chain. So you can see a lack of polar atoms. All you see is just a long chain of carbons and hydrogens, which is similar to what a fatty acid or a lipid would look like, and those are hydrophobic. And that means it hates water. While the polar over here, it means it likes water, by the way. Right, so that's the 4 groups that I separated them into, and these groupings are not like set in stone. So for example, we have a hydroxyl group over here, and that makes the side chain polar. But the fact that this side chain is small is more important than the fact that this side chain is polar. So again, this is not set in stone. It just has been decided that the smallness of the side chain should overrule the polarness of the side chain. And it could go either way, honestly. Nobody cares. It's just a way of categorizing things, and it doesn't have to be set in stone. So before we begin, I think I should explain the red amino acid to you, because they have special properties, and that may make them easier to remember. So why is glycine important? Well, the R is an H. So usually, in every other case, we have a carbon atom surrounded by 4 different groups. as you can see. We have CH3 over here, and CH3 is not the same as what we have elsewhere over here and over here. And same goes with every other R group from every other amino acid. And that makes the center carbon chiral, which means that these amino acids have a mirror image, a different mirror image or a different stereoisomer. That's not the case with glycine because we have a hydrogen atom for the R group, and that means we do not have 4 different groups surrounding the carbon atom because H and R are equal. And that means that glycine does not have a mirror image, it does not have stereoisomerism, and that's what's special about glycine. Next, what's special about cysteine? Well, it's the presence of the sulfur atom over here. And this sulfur atom can participate in the creation of what is known as a disulfur bridge. So what is that? Well, if you have 2 cysteine molecules in close proximity, so what will happen is they will get rid of their hydrogens and they will form a bond between the sulfur atoms, and that's why it's called the disulfur bridge, as you can see over here. So the naming makes sense. Now, why is this important? Well, presumably these cysteine amino acids will be part of a chain of other amino acids, which constitutes a protein, and the chain goes on, let's say it like that. So this is a protein, and we have a disulfur bridge, which what it does is it stabilizes the protein, and it also sort of dictates its structure and its folding properties. So that's why cysteine is important, because its presence could create sulfur bridges, and this sulfur bridge could significantly alter the structure and property of the protein that the cysteine amino acid is part of. Cysteine is the only sulfur containing amino acid. Well, actually, there's another one over here called methionine, but the sulfur over here is not available to bond with because it's connected by a CH2 and a CH3, and those bonds are difficult to break. So we have cysteine over here, which is just SH, and then we have methionine, which is at S combined with CH3, and it's easier to break this bond, but it's hard to break this bond, and that's why sulfur bridges are formed from 2 cysteine amino acids, whereas methionine doesn't get to join this sulfur bridge forming party. It's just left stuck on its own because the sulfur is in shackles by this carbon chain. It can't join in the fun. Alright, what's next? We have histidine. What's special about histidine is it can either be charged or not be charged, and that depends on the outside environment. So for example, if the outside environment is basic, and that means it has a lot of OH minus ions, then the H over here will just join in with the OH minus, and this will be not charged anymore because the H plus is removed. So the positive charge is removed from the histidine. Or for example, we have an acidic environment. There's lots of H plus that can join in. Let's say this is removed. This H plus can join in and make the histidine charged. So it can either be charged or not charged depending on the surrounding and the environment. And that's why I put the question mark over here. Proline. Yes. This is special. I didn't put the A over here because that would just make things a bit confusing. But what's special is you see all these other side chains, they just sort of drop downwards. Well, what's this name over here? Proline. Proline, we have a side chain that loops back around and connects back with A again. So over here we have the R group, but that loops around, it connects with this ammonium group, which is like this thing over here, right? So just R group connects back with this over here to create sort of this structure. And that's what makes it special, right? Everybody else doesn't loop back on itself. This is the only one that loops back on itself. So that's pretty interesting, pretty unique, pretty quirky. And that's all you need to know. The blue ones, there's nothing special to talk about. So unfortunately, they're going to be pretty forgettable. But I hope you have already memorized the 4 special ones, because I sure have. So let's formally begin. Let's set a goal first. The goal will be to recreate this entire table that we have over here from memory. Right? We have to be able to draw the structure and then name that structure. So that will be our goal. And then now we also need a plan to reach that goal. I think a really good idea will be to sort of do the memorization within groups. So we want to memorize, for example, the small group first, and then once we got that down, we move on to the next group, right? So you can see I'm beginning to plan here. Like if you're just blindly memorizing something, you're just gonna like have a list of every single amino acid, and you're not even gonna like sort them or group them or anything. So like you won't even know or understand the relation between these different amino acids, and you're just gonna like read this list and then read it over and over and over again without understanding what these amino acids have in common with each other. And that's just gonna be pretty not useful, right? So this will help us break our job into different segments, which will make it a lot easier. And it will also help us sort of identify the properties of these amino acids. We're not just giving random group assignments, right? These group assignments have meaning to it. This means that these side chains are small, this means that the side chains are polar, and so on and so forth. So aside from memorizing the amino acid, you're also memorizing their properties as well, which is really important. It's like 2 in 1, right? So let's start with the small ones. So there's five of the small ones, right? Five. We have 2 of the special amino acids, and since I gave them sort of like uh, an extensive character background, I've shown you what's special about them, why they're important, why you should care about them, then I think those 2 can be disregarded because you already know about them. Glycine is super special. It does not have an isomer. Cysteine, super special. It has a sulfur, which creates a bridge between other cysteine molecules, which dictates the structure of a protein, right? So glycine, cysteine, right? Okay. The rest we have, I should probably zoom in just so we can focus on this better. So the rest we have CH3 and we have CH2OH. And then we sort of have what we can think of actually as a fusion between these 2. So you can see we have and threonine, which I mean there is sort of a pattern over here, isn't there? Because we have like CH3 and then this CH3 grows an OH and then the same CH3 grows another CH3. So we can think of it as like a Pokemon evolution. We have CH3 and then it grows, the tail grows, and then it grows another one again. So the first evolution, it's an OH or hydroxyl is attached, and the second evolution is a CH3 is attached along with the OH. So that's how I'm going to decide to memorize the structure. Is we have a basic methyl and then we have the evolutions of that. So the name. Well, we have alanine, serine, and threonine. AST. Ala, ser, and threonine. alanine, serine, and threonine. Well, 3, I can just think of it as like the third evolution, right? Threonine, the third. And alanine, serine, alanine, serine. These can just be the other two. Right. I think that should be it. That should be enough, like, sort of bits and pieces of information to, like, and patterns as well, to, like, understand what we're dealing with and to be able to recreate what is in front of us right now. So, let's start. We have glycine, that's the special one, and cysteine, that's also the special one. So, glycine, the A, no, the R group is an H because we don't want it to have a stereoisomer, right? What's special about glycine is it does not have a stereoisomer. So the R group has to be same with either one of the 3 other groups. It has to be either H, NH3 plus, or COO minus. But if it were NH3 plus or COO minus, then that would make glycine charged, and that means that glycine wouldn't have been placed in the small group, right? So that just doesn't make sense. So the only other option is for it to be the H that makes it the same with the R so that it does not become a stereoisomer, right? I hope that explanation sort of makes sense. And cysteine is the sulfur bridge one, so that's this, right? That's this. And the rest is the Pokemon evolution one. So that will be ACH3, that's the first one. And then it will grow an OH. Wait, this will not be 3, this will be 2. Wait, is it? Yeah, it's 2. Uh-huh. And then we have, this will just be CH now then, right? Because it grows another one. So we have OH and then we have CH3. So threonine, because the third one, the third evolution, threonine, alanine, and serine. Cool, cool, cool. So that's the first one down. See, that was super easy. That's 1/4 of our job done already, because there's only 4 groups to memorize. Next, charged polar. There's 8, so this will be pretty difficult. So immediately I already noticed a pattern over here. We have ASP, and then we have another ASP, right? We have GLU, GLUT, and then we have another GLUT, right? So these are related somehow. And not only by name, but you can also see that in the structure as well. You can see that everything is the same, except the O minus is changed into an NH2. And we also see the same pattern over here. And the only difference between these two are the length of the carbon chains. So we have a carboxyl group, and then we have the charged being replaced with an NH2, and then another repeat of the pattern just with different chain lengths, right? So we can think of these two as sort of being related to one another, like cousins or something, right? So aspartate and asparagine. So we know that the ine probably corresponds to like amine, right? Amine is an NH3 group or something like that. I'm not sure. My chemistry is pretty rusty, but an amine group is like something involving a nitrogen in it, as far as I can remember. So that's why this corresponds to this, and this also corresponds to this. So we know that the one ending with ine is the one that contains the nitrogen group, right? So as aspartate, asparagine, that's the short chain. Glutamate, glutamine, that's the long chain. Okay. So, okay, just try to internalize that for a moment. I also need to drink water because I've been talking a lot. aspartate, asparagine, glutamate, glutamine, aspartate, asparagine. Right. So the first 5 things are the same here. And you know that like just and you know that the nitrogen one ends with an "ine" and the one that doesn't have the nitrogen ends with an "ate." So the thing over here is glutam, right? The 5 letters are also the same. So glutam, glutam, and then "ate" and "ine", depending on whether you have an oxygen or a nitrogen. And then we have aspar, aspar, and then "ate" or "ine", depending on whether or not you have an oxygen and a nitrogen. Okay, so aspar and gluta, aspar and gluta, and we have the "ate" and the "ine" that we have to remember. Aspar, gluta, and "ate" and "ine". And then if you just mix the sort of prefix and suffix around, you will get the 4 combinations that you need in order to rebuild or reconstruct these 4 amino acids. Okay, just aspar, gluta, "ate", and "ine, and you just have to know what each of them mean. Aspar means short chain, gluta means long chain, "ate" means oxygen, "ine" means nitrogen. Right, pretty simple. Okay, so that's 4 down, and we just have 3 left. So lysine is 4. It's a pretty long boy. 4, and then Na3 plus. So all of these 3 are positive, right? And positive involves nitrogen. So we know that this thing contains nitrogen somewhere, somehow. Okay. The ring is going to be pretty hard to memorize the structure of, but should be fine. Okay. So histidine, we already talked about it. It's pretty special, so you should have that in your head already. I gave it a nice character background. You should have been emotionally invested into it. Well, as long as you're like a huge chemistry or bio nerd, you should be emotionally invested in to like this histidine character. So let's just focus on lysine and arginine. So they're both pretty long. Uh, we have 4, and then we have 3. So we have 4, and then something that makes a positive charge, and we know that that's going to be a nitrogen, NH3 plus, because typically that's what it's going to be. Whenever some organic molecule has a positive charge, it's definitely going to be an ammonia group that causes the positive charge. So lysine is 4, and then positive charge. 4 plus. Yeah, just think of lysine as 4 plus. Lysine 4 plus. Okay. You have a pretty weird, unconventional structure. So we can think of it as 3, and then we have this thing over here, which if you like turn this sideways, it just looks like this, which is sort of like a carbon, and then like this symmetric structure of a carbon in the center with nitrogen surrounding it, and then the one that it's double bonded to is a positive charge. Right. So we have this structure over here, which I don't know. Maybe we can give it a name just so that it's easier to memorize, like the trinitrocarbon. I don't know. I'm really bad with naming things, but you know what? You can give it a name. I won't bother because I'm just gonna come up with something embarrassing anyway. And it's pretty stupid. But you can come up with a name for this thing. And you could sort of understand it based on the symmetry of the structure and whatnot. and that will make it easier to memorize if you give it like a bit more information about itself. So I guess we can think of it as 3, and then you add that with the structure or whatever. You can call it whatever you want. I'm just gonna give it a triangle because it sort of looks like a triangle, right? That's what I'm gonna go for instead of a name. If you want to follow the triangle, then you can. If you want to follow like and give it a name instead, then you can as well. Whichever works better for you, right? So I'm going to associate triangle with this symmetric structure that I just drew over there. And I'm just gonna like just internalize that a bit. Triangle is a carbon at the center with 3 different nitrogens, and they sort of form a triangle shape, and one of them is positively charged, and it's the one with the double bond in it. That's triangle. That is what triangle means. Okay, let's move on. Histidine, like I said, there shouldn't be any problems with memorizing this one because it's special. So we have CH2 and then we have 1, 2, 3, 4, 5. So it's 5 instead of 6. Wait, where is it? 1, 2, 3, 4, 5. Yeah, it's 5. So it's a pentagon. And then we have just NH, NH on the opposite sides like that. Like that. So symmetric this way. Well, obviously not symmetric because one of them has a double bond, the other one does not. But that dictates whether or not it can be plus, whether it has a positive charge or not. Okay, so just pentagon, and one of the nitrogen has a double bond, and that's the potentially charged one. That's histidine. That's histidine. Okay, let's just give it a rundown back. Lysine, arginine, aspartate, asparagine, glutamate, glutamine. Okay, lysine, arginine. Also note the ene over here. You could utilize the information that you learned over here about ine and ine. Ine means nitrogen containing. So you know lysine has to have a nitrogen inside of it, right? So for example, if they give you this structure, then you definitely know that it's not lysine because, well, it doesn't have a nitrogen inside of it. But then again, this thing has an ine as well. So I guess that sort of explanation is inconsistent. Yeah, that pattern is inconsistent. So maybe we should change it or get rid of it. But I'm just gonna keep at it because it'll be too bothersome to make changes, right? Let's just keep that in mind that the iron sometimes works and sometimes does not. Yeah. I should have planned like more beforehand. But well. Alright. Okay. So there's 7. There's 7. Let's try to do it again. Okay. 7. Okay. So we have the 2 that are related to each other. So we have aspartate, asparagine, glutamate, gluine. So glutamine, right? And this will just be, it's the short one, right? So it's just CH2 and then C. So we have O minus, and then the ine is just O minus replaced with NH2, and glutamate is just the longer version. So we have CH2 and then another CH2 and then the same repeat structure. Right, so we got the 4 of them down. Pretty easy. And then the glutamine is just O minus replaced with the NH2 again. So pretty same, right? You get the point. Okay. Next will be lysine, and lysine is 4 plus, right? So that's just CH2, 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 and NH3. 3 plus. What's the other one called? There's lysine and there's something else. I know that it's 3 plus triangle, right? So that's just this thing here, and then triangle is this guy. And then this is connected with the carbon over here, NH. What's 3 plus triangle called? 3 plus triangle. There's lysine, and I know it ends with an ene as well. Lysine. Lysine. I know the other one is called histidine, the special one. Histidine. Histidine. Is it arginine? Is the other one called arginine? Lysine and arginine. Probably is arginine. I might get it wrong though. So histidine, let's try to draw it. CH2, we have pentagon. Let's draw the pentagon first. How do we draw a pentagon again? So we have this. We have this is the nitrogen H plus, and then we have another nitrogen over here. Just NH. Yeah. So that's histidine. Is it arginine? Let's check. Oh yeah, thank God. It's arginine. Okay, lysine, arginine, lysine, arginine, lysine, arginine. Yeah, when you get something wrong, just repeat whatever you got wrong and make sure you internalize it again. Lysine, arginine, lysine, arginine. 4 plus and 3 plus triangle. Right? Okay, okay. Let's move on. Let's do an easy one now. Let's do a 3. Let's do a 3-membered group. 3-membered group. So again, we can think of this as a Pokemon evolution. Grows a tail, right? Phenylalanine, which actually alanine is this guy, right? So you can see that it's a sort of different branch. Oh, yeah, it is. So like alanine has 2 different evolution branches. You could go through serine threonine, or it can go to phenylalanine and into tyrosine. Because this is CH3, right? CH3, and then it grows a phenyl group or a benzene ring instead of an OH where it does in serine. So serine is OH, this one is benzene ring addition, and this is CH3 again. This is OH. So that's the evolution chain that we go through here. So alanine, serine, threonine, alanine, phenylalanine, and tyrosine. So we can, the T and T, we can just associate that with 3, representing the 3rd evolution again, right? So alanine, phenylalanine, tyrosine, right? So that, see, just try to recognize patterns. It'll make things a lot easier. Okay. Right, so that leaves one other thing. Tryptophan. Pretty similar to tyrosine, like name-wise, but there isn't much similarity when it comes to the structure, so I don't know what pattern I can associate that with. Well, this thing, the pentagon, is this pentagon 1, 2, 3, 4, 5? The pentagon is pretty similar to histidine, and there's a benzene ring. So, yeah, I mean, yeah, I don't see a good way to use a pattern to think about this one. It's just almost seem like histidine, just adding a benzene ring. Tryptophan, you call it tryptophan. Okay. Right. This should be pretty easy. I mean, we have phenylalanine, which is CH2, and then the evolution is you give it a benzene ring, and then we have tyrosine, that's the third evolution, so it grows in the hydroxyl tail, right? And then we have, I hope I can draw this right. What does it look like? Like this, right? Yeah. And was there a double bond? I know that this has an N in it, but I don't think the N has a double bond. I think the double bond is over here. So that's tryptophan. That's tryptophan. Did I get the double bond wrong? I got. Ooh, I got. I'm not sure, like, if because I drew like this on the. Yeah, I guess that makes this whole structure different. Yeah, so it has to be like what? Like towards the left, right? Because I drew like the connection over here, like in the center over here, as you can see. So it has to go down and then branch off to the left. Like you see, I draw it like that, which is wrong. So I have to do it like this. The double bond is over here. This is the N. This is the benzene ring. Right? Gotta pay attention to these minor details. Am I still recording? Yes, I am. Okay, good. Good. So, phenylalanine, tyrosine, tryptophan. And that's 3 down. We have 1 left to go. See, you don't have to spend hours upon hours of memorizing. You can make this fun. You can come up with different names, different Pokemon evolutions. Like these are the strategies that you have to come up with. And it's fun. It's better than reading a list over and over and over again, right? And you get to learn more. It's much easier to remember and associate to. So, valine, I see similarities with like alanine. It could just be like another evolution thing, right? Because like we have like could it be? It's like alanine grew. Uh, ah, Jesus. It's like alanine grew 2 extra stuff over here. So we could think of it as like another evolution, but I don't know, maybe we'll be like overloading that strategy too much. Like if you add too many details into like a strategy, it just becomes obsolete because it just becomes too complicated. So it could be like its own thing. We don't have to like associate it with the alanine evolution tree family thing that we currently have. So we have valine. Okay, that's just like a thing like that. Guess. I guess it's like hmm, like a V, like an upside. I mean, it's an upside down Y, but like this is a V structure, right? So maybe V. Okay, maybe. Right. I think I'm just gonna stick with that. I just ran out of water. I'm gonna go get more. I'm back. Okay. Okay. Hold on. Okay. 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 So that's valine down. We have leucine and isoleucine. Clearly, they're related to each other. The name suggests that, and they are, because they're just isomers, structural isomers of each other. They just differ in the placement of this methyl group. This methyl group is at the second carbon. This methyl group is at the first carbon. Right. Leucine, valine, leucine, isoleucine, valine, leucine, isoleucine. So leucine, well, it has this thing, which I guess you could say it looks like an L and then another L. It's two L's combined. I don't know how useful that is. And then we just have isoleucine, which is just this moved up here to make an F. Is that analogy useful? I don't know. Leucine, isoleucine. Well, isoleucine looks more like an L. Looks like an upside down L, right? Yeah. Isoleucine. Isoleucine is an L. Leucine drops down. Huh. Can we make a story out of that? Or an analogy? Like, iso means. What does iso mean? Like, iso could mean good. Like a good leucine, because it actually represents an L, and then you remove the iso, and it doesn't become an L anymore. It just drops down. It falls down. So the iso is what fixes the leucine. So iso is good. I don't know, man. I'm not the best at coming up with strategies. Some of them I really like and I think are good, like the Pokemon evolution one. And some of them are just bad, but I'm not creative enough to come up with good ones. So that's just leucine and isoleucine, I guess. We have methionine. That's just let's just think of it as a worse version of cysteine. It's like cysteine and then you put it in like handcuffs, the S. You put S in the handcuffs so it can't do anything. Right? And you call it methionine. Methionine. Cysteine, methionine is the worst version of cysteine. Methionine. Methionine. How do you go from methionine into worst version of cysteine? Like the name. How do you relate the name together? I guess I don't see a way. Methionine. How can meth correspond to a worse version of cysteine? What does meth mean? Well, meth means meth, crystal meth. And crystal meth is bad, so that's a worse version of cysteine? I don't know, man. But yeah, let's just leave it at that. I think I got this down already. And proline is the special one. The special one. Another pentagonal structure, pentagonal ring structure there. I think I got it. I think I got it. Yeah. So you have valine. Valine is the one that's a Y. So that's CH2. Wait. That's A, CH2, CH3, CH3. That's valine. And then. Oh, wait. Wait a minute. Because, like, if we add another tail over here, this turns into isoleucine, right? This is isoleucine. This is the L. This is the L thing, right? That's isoleucine. So it could be valine evolves into isoleucine, and then you get rid of the iso, and that corresponds to this dropping down over here. Because iso is what keeps everything together. Or like that's the meaning that I invented to give to iso. Like it keeps things together. You remove it, things fall apart. Okay, cool. Alright, so that's valine, leucine, and isoleucine down. So you can think of it as another evolution tree, if you so wish. What else do we have? We have the bad version of cysteine. We have methionine, which is just, like I said, cysteine, but the S is in handcuffs, so it can't do anything. Right, that's worst version of cysteine, methionine, because meth is bad. Okay, cool. Proline, that's the special one. Right, so we have, how do we draw this? Well, we have the, wait, no. We have the COO minus, we have the H, and then we have the NH. This goes down like this. This is NH. Should be 2. Wait, or is there a double bond? Is there a double bond? Is there a double bond? There is no double bond. Okay. Proline, that's proline. And that's everything down. Right. So let's go through all of them all at once now. Right, let's start with small. There's 5 small. There's 5 small. There's 7 polar. There's 3 aromatic, and there's 5 again. 5 again of the hydrophobic. Right, let's start. Glycine. That's the one with an H, because it's not a stereoisomer. We have the evolution tree. We have alanine, serine, threonine. That is CH3, and we have CH3 grows in OH, and then we have this grows in OH and another CH3. Right, and then we have one more. That's another special one. That's cysteine, right? Cysteine. That's the CH2 and then S, and then this S is a sulfur bridge. Right. 7. Right, this is the gluta aspar 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 glutamine, glutamate, asparagine, aspartate. So this is, wait, gluta is longer one, aspar is shorter one. Yeah, so CH2, C, O, O minus, right? That is 8, 8. And ine is the nitrogen containing one. And gluta is the same, but the only difference is you add another thing, so that makes it 2. Okay, yep, that's 4 down. Super easy, 4 down. 3 left. One of them is special. That's histidine, because it can either be positive or not. And you draw that. How do you draw that? Um, it's pentagonal, and I know that the double bond is over here. There's a double bond at, no, not that, it shouldn't be. Wait, this is the NH plus 1. There's a regular N. Is it like this? Or is it like this? Like this. Like this. Right? Maybe? Maybe. Wait, but if I look, then I will see the other 2 as well. There's 2 more. And that's the 4 plus and the 3 plus triangle, which is, no, I was about to say leucine, but it's Leucine Isoleucine, which is part of the other group. Alanine. Alanine? Have I used alanine before? Oh yeah, alanine, yeah. Crap. Uh, what's 4 plus and 3 plus triangle? Um, Leucine. No, wait, leucine is this. Leucine and Isoleucine. I said leucine already. Um, Arginine. Arginine is this one. I know this one also has to end with an "ine." Valine is not. Valine is this guy. And then leucine is this guy, and isoleucine is this guy. So what "ine"? Glycine. Right? Glycine arginine. Cool. And 4 plus is just CH2, 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 blah blah blah, and then NH3 plus. This is CH2, 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 and then the structure, no, it starts with an N, H, C, double bond N, H2 plus, and then NH3, the triangle structure that we talked about. Glycine, arginine, histidine. Let's have a quick look. Wait, it's lysine? Oh, leucine and lysine. God. Yeah, those two are super similar. Lysine. Yeah, lysine and leucine are pretty darn similar to one another. That's why I thought, yeah, lysine, leucine. You have to. Let's keep that in mind. Lysine and leucine. Lysine, leucine, lysine, leucine, leucine, leucine. Right? That's how you spell it. Yeah, leucine, lysine, leucine. Okay, okay. So that's one mistake because of similar names between different groups. That's why I didn't catch that. Um, so that's 7 down. 3 is the aromatic. That's the different evolution line of alanine. Phenylalanine. It grows a benzene ring. And then tyrosine. That that's the benzene ring, and then plus the OH. And then is it the special one? No, it's not the special one. It's tryptophan. And that is the one that I struggled to draw with. It's CH2, and then I said it must be towards the left. So we have, is the N at the bottom? It should be. And then where's the double bond? Does it have a double bond? Does this part have a double bond? I think at the top. And then that's it. Ooh, didn't mean to do that. Nope, it's just directly to the bottom. So that's tryptophan. Tryptophan. Okay, okay. 5, we already did the 3 over here. So the 2 left is worst version of cysteine. That's methionine. That's CCSC. Sulfur in handcuffs. Can't do anything. And the next one is the special one, proline. That's the C. We have COO minus. We have H. We have NH2 plus. There's no double bond here. Yep. Looks something like that. It's proline. So that's everything down. Right. And this will probably stay in my head even after I sleep, even after a few weeks, just because we had a bit of fun while doing it, you know, coming up with different patterns and ideas and creativity with like different naming systems and such. So it's a pretty, it has personal attachment to it. You're sort of building and creating a system of sort of obtaining data and forming patterns and coming up with different strategies like Pokemon evolutions and stuff. Like this becomes something more personal. Like I think if you just follow along with my strategy, it will be hard because like maybe you hate Pokemon and that's why the Pokemon evolution thing, or you're not familiar with Pokemon evolution, and that analogy or that strategy and technique doesn't work well for you. So it's always best if you come up with ones on your own, right? Because that will make things more personal. There's personal attachment to it, and that makes the information retained for much longer. I'm just rambling at this point now. God damn it. But yeah, I memorized almost everything. There were a few mistakes, because there always will be mistakes, but that's part of the process. You can't just perfect everything. Life's not that easy. But yeah, this is how I do it. It works. See, it works. And you, I suggest you at least try it as well, because it's really super duper helpful. It's really super duper helpful. That's all I have to say right now. I'm really tired from talking. Um, okay. I hope this helps. Yeah, I hope this has helped. You can feel my brain cells slowly dying. I'm struggling to hold a basic speech because I've been talking for so long, and it's really late in the night right now. Okay, I won't say anything anymore. Goodbye.